Okay, so first of all, thank you for staying. Secondly, let's speak a little bit about memories. Do you know what is the best memory ever built? And you cannot have a look to your notes, huh? Otherwise you will be cheating. Built by the human being. No? No? Ever? No? This brain. 10 to the 11 neurons. One of the most powerful machinery we have, right? We have short-term retention and long-term retention, depending probably a little bit on our age, right? I was busy yesterday preparing my slides, and my wife was complaining that basically, according to her, my memory had the data retention limited, and the data access limited. It turned out that I forgot to take the bin out on that day, right? So all of this actually shows that, I mean, we have different type of memories working in the system. Now, what is interesting to see is that to say have some follow-up, to have a look to the how memories evolved through the history of electronics. I like doing a little bit of science or engineering archaeology. So the very first, no, it's not the very first, the second memory that have been generated, which was basically produced in mass, to be non-volatile, was basically paper, a pencil, right? If you have a cost per bit, it costs something around $0.75 per megabit. Relatively cheap, huh? That's very difficult to beat. So that's one of the reasons why, I mean, people have been using, aside from the fact that there is no electronic and probably no alternative, aside from rocks, but people have been using this really, really, really a lot, up to 1946. Why 1946? Because 1946 is basically the advent of the first supercomputer, the ENIAC. You're too young, and me too. I've never seen this machine working. But basically, at that time, the memory was actually a paper card with punches. They were using it for memory operations, but also for logic operations. So you had operators spending their days in punching holes in papers to make mathematical operations. Still at that time, pretty cheap for the memory, around $0.75 per megabit. Then we made a big step forward, 1967. The first floating gate in the system, 0.2 kilobits. Big step forward, $15 million per megabit, right? So it's a pretty expensive exercise, especially if you want to have 128 gigabytes in your cell phone today. You don't make it. But quickly, thanks to the scaling and the reduction of the dimension of the system, people were able to keep on reducing the cost of the memory. You see already, 4 years afterwards, the first EEPROM, which was 2 kilobytes generated by generated by Intel, already the price dramatically reduced. Still $500,000. You need to be very rich to be able to have this kind of thing. When I made the slides, it was 5 years ago, 128 gigabytes, at a cost of 10 to the minus $5 per megabit. It's almost nothing, right? We managed doing this by reducing actually the device dimension, but also the manufacturing cost. So you know how a memory is working? Yes? No? Aside from our brain? No? So typically you get something that looks like this. We have metallic lines. That's basically what we call the contacting lines in the system. So the pink ones are insulator layers. On top of this, we have typically the flash memories you have in your cell phone, looks something like this, where basically you have doped silicon. You have an oxide, which is typically silicon oxide. You have a floating gate here, which is typically a charge trapping agent. Then you have a top oxide on top of it to insulate it from a control gate. And then basically what we have is these blocks being present and repeated everywhere. So this is still a two-dimensional technology. Now we are working and stacking them 3D. That's how your density is increasing in your cell phone. This is actually, you have controllers, and then on top of this you have other lines. So you have the bit and the word line here that basically you get something that looks like this. You have a top view of the system, where basically when you apply voltage along this line and this line, you have a crossing point. The crossing point is the part of the memory that you are basically switching on and off. How does it work? Well, you start injecting an electron from your control gate. Because your top oxide is relatively thin, you can, with the potential you are applying to your system, tunnel with the electrons or the holes, depending on the type of memory, through it. When you switch off the current, the barrier is back, so the system cannot the electron on the charge cannot escape anymore. Then you write your memory or you read it. It could work something like this. You trap any system. So we've been working with these non-volatile memories, and I think that this type of technology is never going to die, because I mean they're so cheap to produce that people control correctly this interface in a so nicely way that they will keep on introducing tricks to speed up the operation of the normal memory. But just to show you how it looks like, I mean we end up to basically very narrow trenches. You see very deep ones. I don't know if you can read it properly, but okay, you have your insulating gate somewhere here, your bottom gate. So you see you have some idea of the control that you have in internal morphologies of the system. But of course, these memories are extremely complex. So this is another type of memory. This is so-called volatile memory. That's basically the memory which is present in your computer, the DRAM one that you are using, where basically the size of the trenches is way, way, way deeper in the system. And this is basically what you see over there are the metallic lines that we are also using to address the transistor for logic applications. So just to show you the complexity of this thing, you see that this section here is actually this small block lying below, and then you have different lines, metallic lines on top of it that we need to control. All of this has a packaging on top of it, and then we start stacking them all together. So there is very obviously a matter of dimensions. I'm just going to try to explain you to give you a human scale relations that we have. I don't know if you know what is the deepest trench which exists on Earth in terms of dimensions, but that's basically the Marina Trench, where basically the aspect ratio, so the depth over the width of the system, is basically something around 36. Yes. Now one of the tallest buildings ever built by the humankind, and that's the aspect ratio, which is about 8.2. So this gives you an idea about the dimensions we're discussing, right? So this is 2,500 kilometers, about 70, right? Around here. Flash memory, the aspect ratio is 10. So roughly the same ratio between the Burj Khalifa structures. For memcap memories, we have an aspect ratio of 163. So it's extremely complex, extremely deep. So there are a lot of challenges in terms of structures. We have high memories in the system because we coat all of them with a high dielectric constant material. And that basically gives us a high capacitance because we have a high surface. The problem that you have is that the memories that we have been having so far you need to have two types of memories. You have one memory that will just keep the information, the non-volatile memories, the flash, the SSD that you typically have in your cell phone. And then you need to have something that works faster. You need to have something that works faster because when you work with a CPU, you need to be able to exchange a lot of information to store them. And then the non-volatile memories, they are doing a very bad job for that. So we have typically the DRAM structure. The problem is that today, this guy here and this guy here are somewhat reaching their limits. Because we like to have them working as fast as possible with the highest density as possible in terms of data storage. If you have a look to the morphology of this, okay, we start stacking them, but at a given moment we won't be able to keep on putting layers and layers and layers on top of this, because mechanically the system is going to be so fragile that it will collapse. We are already facing this kind of problem today. On the other side, this guy here, we cannot make the trenches deeper and deeper and deeper because there will be no matter anymore, right? And also, we ideally need to be able to increase the dielectric response of the materials we're using in the system so that it gets larger and larger. And we know this is extremely challenging because most of the insulating oxides we're dealing with have a dielectric constant that typically range between 20 and 40. Beyond that, there is not much that can be used. So ideally, people have been trying to combine the two, coming up with new device concepts. So just to give you an idea, that's a little bit the zoo of some of the activities that people have been working on, and I'm just going to touch two of them. One which is called resistive, the memory store-like behavior, so resistive random access memories, and MRAM stands for magnetic resistive access memory, random access memory, I'm sorry. So how does it look like? Well, typically, that's what I told you at the beginning, that we are going to trying to work with the dielectric, but trying to change the materials that we are going to use in such a way that we control the resistance state. So we don't store charge anymore, but we just make the life of the dielectric between the electrodes so miserable that basically it will all of a sudden conduct electricity or not. I mean, for people familiar in that field, that's something very close to the electric breakdown of the system. For the magnetic memories, we have order integration challenge, and I will illustrate how the simulations can help you to understand, for instance, the chemistry you should be using. So we're going to have a short trip to this to understand how these atomistic simulations can give you some understanding of how to make these filaments and how these memories are working. Okay, so let's have a look first to the memory store memories. So as I told you, the working principle of one of the prototyping memories is the following. So you have a metal, an oxide metal. We apply a very strong field present or a strong voltage present in the system. And because of this, we are destroying, in a way, we are changing the chemical compositions of this of the oxide. Basically, we are making semi-conducting or purely conducting filaments. Whenever the filament is touching the two electrodes, basically the current is flowing from metal 1 to the second electrode in the system, so you have a current on in the system. We are able to control the size and the dimension of this filament, and we can basically build a rupture or not in the system. If I build a rupture, there is no current in my system, so I have an off current, I have high resistance state. I build a system, so I make something more less resistive, and then I can start cycling. You see, I can operate this. The whole record is 10 to the 9 cycles there. Okay, so problem is that, because I'm speaking a little bit of old stuff that we did in IMEX, so we worked on that 8 years ago, that's to try to understand how you can control the formation of these filaments and actually how this memory is working. So there are actually a lot of different questions that were raised. So first one is that, okay, what kind of mechanism basically is at the origin of the switching? In our case, basically, we're going to study a case of hafnium oxide sandwiched between two metal electrodes. Then is there a dependency? If I use different metals to my bottom contact or my top contact, is there a dependency on the operation of my devices? What is the speed of the switching in the system? Is there a kind of diffusion process or something else? So basically, you can use these atomistic simulations to get qualitative insight in what's going on. I spare you this, that's modeling slang for you. But basically, we have been generating hafnium oxide models, and typically these memories work nicely when you work with amorphous materials, so in this case amorphous hafnium oxide. And how do we build these models? Simply how we proceed in the same way as you would proceed experimentally. We heat a system, so we heat the oxide at a very high temperature, completely unrealistic, and then we cool down quickly. A bit similarly to what you would do to build glass out of silicon oxide. Okay, so how does it look like? So the memory that you saw over there, that was actually generating this behavior, is basically the same stuff as you see here. So you see here the top and the bottom contacting line, and typically we work with a metal which is called as titanium nitride, deposit it in contact with hafnium oxide, and you see that on purpose we put a little bit of hafnium here. There is a good reason. I'm going to try to explain why. So first, the simulations can give you some idea about how the band diagram is looking in this complex stack. Titanium nitride, some kind of hafnium or hafnium suboxide, hafnium oxide, titanium nitride. It gives you how the band alignment is working. And because you know the band alignment, you can have some idea about what thermodynamics or what you decide to do this, in the system by applying an external voltage. So this is basically what you call the formation energy. So this is the cost in energy you need to provide to the system to make a defect. And there can be a lot of different types of defects. You know, you have hafnium oxide, so you can remove hafnium atoms, you can remove oxygens, you can inject oxygens, you can inject hafniums. Then perhaps you have also some titanium or some nitrogen diffusing in the system. So by using these simulations, basically what you can have an idea is you can have some idea about the operating voltage of my system. So this position is the top of the valence band, this one is the bottom of the conduction band. So I start operating my voltage here. This is the position of my Fermi level for titanium nitride. And then if I lower the voltage, I'm going to sweep along these directions. And this simulation tells you, look, if you assume that, for instance, you have an hafnium interstitial diffusing, so this beast is diffusing in the system, that's the amount of energy that will cost to generate it. So anything positive means this is not going to happen. Whenever it is negative, spontaneously negative, it means that spontaneously you set your system by the external voltage in such a way that you will start injecting particle in your hafnium oxide. So what the system tells you is that, look, first, if you don't put your voltage too low, I have a tendency to inject oxygen, negatively charged. So it's a moving species in my system. You see that's negative here. If I put my voltage even deeper and deeper along these directions, then spontaneously, very close to the top of my band, I will start generating spontaneously oxygen vacancies, and will also start injecting hafnium in my system. Okay, so this is for a perfect crystalline phase. It already gave you a flavor of what's happening. If you operate the voltage in the other direction, spontaneously you start injecting oxygens in your system, negatively charged. But of course, all of this depends very much on the conditions you are using. When we basically grow these materials, we typically work in the conditions where the partial pressure of the reactor is extremely low, meaning that you are pumping. And because you pump in this, basically you tend to release oxygens a lot. And you see here that if I work in very low partial pressure in my system, I start to dissolve a lot of oxygens. So basically what I have is not a perfect hafnium oxide, but it's already in the situations where basically this is a lot of oxygen vacancies present in the system. Ever more importantly, on top of this I start sputtering hafnium to make my contact. So what happens? You put a metal in contact with an oxide, guess what is happening? Basically you suck oxygen out of the oxide because the system wants to be at the chemical equilibrium. Basically what you observe is that depending on the partial pressure which is present in your system in terms of hafnium, you spontaneously start depopulating here. You see the enthalpy of formation is negative, so you start depopulating oxygen from hafnium oxide to make some kind of suboxide. So basically what you are building in these devices here is hafnium oxide, hafnium suboxide, hafnium, titanium nitride. We can also check the speed at which all of this is occurring. Remember, we've been discussing the possibility of also having a little bit of hafnium diffusing the system. Now we have two contenders, oxygen diffusion, oxygen vacancies, or hafnium diffusion. But all of this depends on the speed at which this is occurring. Thermodynamics give you an idea what the direction it takes. It can take the age of the universe to be there. The kinetics will give you an idea about the speed. So what you see over there is that we have been evaluating the activation energy. So how much energy, how much time is it going to take? The larger the barrier, the slower the process. Basically what you observe is that for hafnium here, the activation energy is about 3 eV higher than the one of oxygen. Meaning what? It means that you take the edge of the universe for the hafnium to diffuse in the system, while oxygen is very mobile. So the guy which is actually responsible for the diffusion here is oxygen interstitials or oxygen vacancies in the morphology. Okay. Now question is how much do you need, right? And you can use these simulations to get some idea about the concentration. So what you see over there is the evolution of the electronic structure of hafnium oxide upon the insertion of different percentage of oxygen vacancies. If the concentration is low, basically you get an isolated signature of a defect. A single oxygen vacancy is not doing anything in your system. But then if you start operating and increasing the amount of oxygen in your system, time, you start making a bend. Meaning what? That the defect here starts speaking to its neighbor, and then the current will jump from one to the other. And then if you go towards an extreme case, you see that basically the system is getting completely metallic, which could be one of the explanations why when you are sweeping your system, you go from a high resistance state, so the oxygen vacancies are separated from each other. Then you make some kind of conducting filament, they are getting a little bit closer, and then all of a sudden the current is going through. So the answer in terms of concentration is that you probably need something at least lower than 12% of oxygen vacancies. That's a lot for MyVideo. So basically we quantify this, and it turned out that, I mean, by combining the simulations versus the XPS signal in terms of measurement, we discovered that only 5% of oxygen was actually removed from the hafnium oxide during the deposition of hafnium. And that is, I mean, in a way, consistent with the fact that you see that there is some kind of transfer into the mechanism for the leakage current, so the operation of the device. Okay. So, but all of this depends on the type of metals you set in contact with your system. So what do I mean by this? Look, we are sputtering a metal on top of your structures like this. But perhaps if you use different metals, we can have a better memory or a worse one. Right? Ideally, we don't want to remove too much oxygen. Otherwise, you don't control the way your device is operating. So if you evaluate the enthalpy of reaction, so how much energy it costs for the system to remove oxygen from hafnium oxide. And if I plot the type of metals versus this, you see that for hafnium and titanium they are relatively equivalent, so they are keen to take oxygen out of the system. While components like tantalum, aluminum, or even worse platinum have little tendency. It turned out that basically we tried all of that, and you see over there that if you use a tantalum capping layer, you see that basically the device has something that works a little bit, and the retention is very good, but basically you cannot switch a lot your device operation. Ideally, you would like to be somewhere here, on the other side of the plot, somewhere on the wall. So by playing around by the type of metals, it turned out that basically having hafnium deposited on top of hafnium oxide gave you the best trade-off in terms of data retention. So how long you want to keep your data on your flash or on in your memory before you lose it, and basically the number of times you can cycle it. So basically it turned out that having hafnium oxide basically deliver you the best performances. But what you saw so far is built on some kind of crystalline perfect system. In practice, I told you that we hardly work with this. We typically work with amorphous one. Why? Because you don't want to have a memory that needs 10 volt to be operated. Because if you work with amorphous structures, the easiness of making your defect, the formation energy to remove an oxygen in the system, is actually improving, because you get a broader distributions in the structure of the materials. The number of times the oxygen and the hafnium are coordinated are different. Because of this, you reduce basically the voltage you need to apply to your system. Here, for instance, you get about 1 EV in gain. Aside from that, what is also very important is to try to get some fundamentals about how the elements are diffusing in your memory. For this, you can also get some information using atomistic simulations to try to see the speed at which the oxygen will diffuse, depending on the composition, because sometimes it can vary. You have hafnium oxide, which is here, which is not uniform, then you have an oxygen gradient and interface, and perhaps it diffuses faster on this side and on that side. Nobody knows, right? So you can actually simulate, using atomistic simulations, different oxygen concentration in your materials, going from the oxygen poor conditions towards an oxygen-rich conditions. And then you proceed as you would proceed experimentally, that is to say that you measure the diffusion length of the oxygen versus temperature. You have an Arrhenius plot. Out of that, you can extract the activation energy. And basically what you observe is that the oxygen, well, I mean, they diffuse, no? And then the poorer it is, the faster it diffuses in terms of oxygen. So this tells you what? It tells you basically that when you start moving here around, whenever the oxygens are present in the hafnium, then you have less control on the distribution of our hafnium, the oxygen in the hafnium. They will start diffusing a little bit everywhere. So you don't want to have it too thick neither, otherwise your memory is not going to have the retention and the cyclability that you would like to have. Cyclability actually implies that we need to be able to inject back the oxygens in the system so that we can switch on and off this filament present in the system. So we need to be able to keep it back. So they cannot diffuse too far. So there is actually a thickness dependency of the system is behaving. So what is also very important that you don't want that the oxygens start diffusing too far away. And you have other type of metals contacting them, like titanium nitride. The good news is that basically you see that if this is pure hafnium, the oxygen doesn't want to diffuse inside, it's extremely slow, so you have a barrier against oxygen diffusion. Would there be an accident and then some oxygens are still lost over there, in titanium nitride is also extremely slow diffusion. So that's good news. It's one of the reasons why the memory is working. Now how do we operate it? A small movie for you. So we start with this memory, with this filament, then we inject the oxygens in the system. How long does it take for the memory to switch on and off, which is extremely important? Well, the simulations will tell you, and I hope it will work. Yes. Oops, wait. Okay. So what you see here is the electronic structure of the system. This is hafnium oxide. Okay. So the peak here, the 0 is set at the top of the valence band. This is the bottom of the conduction band. And in this case, what do we have? We know we have oxygen vacancies, and we know we have oxygen interstitials. They are moving around, right? And what you all would like to understand is when I'm moving from the situations where I will start injecting oxygen here in the system. So basically I have missing oxygen somewhere along this filament, and the one I'm going to inject, well, they want to speak to each other to recombine. And that will give me the speed at which my memory is going to operate, on, off, okay? So you would like to be able to track the dynamic of recombinations. That's basically what I'm going to show you here. So what we did is we made, you will have to believe me, the purple area is missing oxygen, and we put an oxygen interstitial here. And ideally what you would like to see is that this guy diffused up to here to see that basically there is no defect anymore. The purple area you see over there is a signature of the defect. Okay? No defect means that basically the position of this peak, or you will see the different peaks in your band gap, all of a sudden these peaks are going to disappear. It means that the material recovered from the defects. Okay? So we use a technique which we called atomistic molecular dynamics, where basically you will see here times scale. So you see at the beginning there is nothing, so you have two peaks present in the system. The system starts vibrating. So only a few femtoseconds. And now look, they vibrate again, 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 and oops, no defect in your band gap anymore. Have you seen the oxygen moving? No. So what's happening is that simply you have an amorphous structure. Okay, the vibrations corresponds to what? The bonds that are present in the system. And because the system is vibrating, the system is all of a sudden realizing, ooh, I'm missing some bonds over there. And because of the vibrations help changing the local coordination in the system. And because of that, you have an extremely fast switching in your memory. Okay. So we can also use these atomistic simulations and the insight that we get in order to try to understand the electrical signal which is present in the system. So one of the problems you have with this type of memories is basically that when you set a certain voltage in your system and then you measure the time, you see that basically the current you get fluctuates through time. You see over there? It's basically what we call the random telegraph noise in the system. A perfect system should have a flat line, meaning that the current is constant independently of the time away, right? But in practice it changes. Why does it change? Because actually what you have is that a little bit of the oxygens is diffusing through time. And every now and then, basically, what you get is that you are basically moving from one filament, which is basically this one, to another one. And the size will be different, the oxygen concentration will be different, the current is going to be different. So you get some random, modulations of your signal, which is not very good for memory. So today we're using this technique to develop encryption for banks, because this is completely random, so that's way better than any electronic system that you can get. So sometimes a failure is a benefit. Okay, so all of this to tell you that basically using these kind of techniques, you can get fundamental insight in how the system is working. So you can get information about the forming process of your memory. Look, with oxygen filament formations in the system, you're storing a little bit of oxygen in your hafnium buffer layer. Depending on the voltage you're applying, you inject back the oxygen to the system. They make high resistive or low resistive state. You build back your filament, and basically you can start cycling on top of this. So why is this interesting? Because, I mean, of course, though the retention mechanism is complex, I mean, some of the technologies have been used today in the Optane memory processor, the Optane memory that people have been developing in Intel. They've been using a similar technology, this is not the hafnium oxide base, in order to be able to select and address specifically a memory using the modulation of the chemistry present in a system. Okay, this is one example here, but I have another completely different example on how you can use the simulations for magnetic memories. So there too, we are interested in understanding how we can switch a state in a memory which goes from a low current to a high current. In this case, we're going basically to use magnetization. So the magnetization which is present in the system is what? We are basically going to use two magnets, which is typically cobalt iron boron, sandwiched between magnesium oxide. And we are going to apply a voltage or current in the system, and thanks to that we can change basically the orientation of the magnetization in one layer, the one on top of this. And basically the current we measure is the tunneling magnetoresistance. So the resistance against the tunneling in the system. Different magnetic properties means basically a very efficient operation in terms of memory. Okay. In practice, this guy here looks like this. This is a nightmare with about 20 different materials being deposited there. I told you the memory is about 85% of interface there. This is nightmarish. So we don't necessarily understand all the physics and all the material chemistry which is present there. But we need to be able to deposit it, and we need to be able to etch it. Because typically the way we work is we deposit pretty broad films, and then we dig holes in the system to make scale dimensions. And you will see that's a misery. There are a lot of technical challenges being present there. One of them is, of course, you need to be able to deposit the materials you want. Sometimes at the sub-nanometer thickness. I have some of my colleagues making the claim that they can control the thickness composition below 1 angstrom. Do you believe it? I don't, because 1 angstrom is smaller than the size of an atom, right? But I mean, actually, the numbers in terms of surface roughness are below that, statistically. Okay, so we have a good control there. But it doesn't stop there, right? Because actually, of course, you need to find the right materials there. We have a lot of activities in order to try to find the best one. You need to be able to control correctly the quality of this oxide. No defects in the system. As thin as possible, but not too thin, otherwise you get leakage current from the two sides. This is a texture material. So this works only if your magnesium oxide is crystalline. And to be crystalline, you need at least 10 different materials below. You need to also to be able to control the magnetization. For that, you need to introduce a lot of different layers in the system. And all of this combined to what? Thermal stability, because you don't want that if you let your cell phone in the sun that all of a sudden you lose all your pictures. And also that basically we need to have the lowest current as possible to operate the device. Why? Because again, we don't want also to move around with 2 suitcases of batteries, right? And ideally, we hope to be able to use this kind of principle of memories to be able to reduce the electricity consumption that we need for the cell phones and other type of operations. Okay, so let me illustrate one of the other problems we have. Say you want to dig a hole in this. How do you proceed? Well, normally the way we would proceed is by sputtering. So basically with a plasma, which is a gas charged with ions, and then we apply voltage, and then we use the ions to bombard the surface as much as we can. And we know how to control the angles of the bombardment in such a way that we can have, hopefully, a control in the shape. You don't want to have it flat like this. You also don't want to have it like this. You want to have it like that. Well, the main problem that you have is that while we know to do this on silicon oxide, or even in germanium, for most of the metal we have, we observe that there is basically a lot of residues being deposited on the sidewall. Okay? And this you don't want, because I mean these residues, they can shortcut your device, they can generate a lot of chemistry problem in terms of stability and reliability in your system. So you will tell me, how is this modeling going to help me? Well, I mean, modeling can help you because basically it can give you a hint about which chemistry you should be using in your plasma. And how likely is it to make volatile component or non-volatile component during this edge chemistry? So for this, you need to use thermodynamics. And I'm going to spare you some of the details, but basically, the thermodynamics, as we already discussed, give you about a feeling of the direction that the chemical reactions wants to take. Say you have A plus B, that gives you C plus D. If you release energy, spontaneously the reaction is going to take place. Okay, you might have to wait the age of the universe, but if this is positive, it will tell you no way. Okay, so you can actually evaluate the contribution of temperature and pressure that you have in your plasma by computing each of the ingredients, which is normally something you do using statistical thermodynamics and physical chemistry. Here again, no need to go into details, but basically you can get the contribution which is present here for different temperature and pressure. And you will, as you will notice here, you have a term that depends on the vibrations of the system. And the atomistic simulations can give you very accurate contributions of these vibrations. As you can see over there, this is the phonon density of state. So a phonon is like a frequency of vibration, just in physics. Where basically you see that the dots over there are actually overlapping with basically what is simulated. And we can evaluate that for different temperatures. So you can really simulate the process of the system. So you have actually two contributions in this enthalpy of reactions. You have a term that depends on the energy. So which is basically, if you plot what is known experimentally versus what you compute, you see that they match very nicely. And you can also get this contribution of the entropy for pressure and temperature, where basically you see that what you compute versus what you measure is also matching very nicely. So what you can do is that, given that you know the chemistry of your system, you know what kind of metals you're interested in, edge, you can now try to build a very extensive database of chemical reactions. Again, I will spare you all the details here. But we found a way in order to evaluate all kind of volatile solid component that could be generated, and I will show the example of cobalt iron in the system. Evaluate this database, and then we have something that we call a reaction generator, taking all the component, equilibrium, basically the system is trying to equilibrate all the chemical reactions, and then you end up to something around 800,000 possible chemical reactions. And then for each of the reactions, you would like to know the temperature and the pressure. So you end up with a grid that looks like this, right? So you have a lot of points in the system. For ideally for a range that goes in terms of temperature, pressure dependency. Well, so typically you would get a plot that will look like this. This axis basically shows the temperature effect. Okay, the color scale is the pressure effect. And basically what you observe in this axis here is the likeliness of making a solid or a gas. So this is basically, if the value is positive, it means that the difference in energy to make a solid is basically positive, so making that the system wants to be in gas phase, or the other way around. So basically you have a color plot that basically, in this case here, tells you that you would like to have this value as low as possible, and it's, in this specific case, it's only possible for low partial pressure, high temperature. So you filter all of that, spend a lot of time in doing this, and then you inject the chemistry you're interested in. What kind of chemistry you would like to have? Well, I mean, you would like to use halogen-based chemistry because that's something which is plasma friendly. Hydrogen, oxygen is typically present there. We can also start injecting nitrogen or organic molecules in the system, hoping that the plasma is going to split it up and helping the reaction in the system. There are drawbacks of some of this because, for instance, chlorine is so aggressive that it attacks the steel in the reactor that you will be using. You check different formations in this case. We're interested by cobalt iron, so you can make solids, different phases, different components in the system. You check the chemistry of the system, so you end up with this long list that you can have. The thermodynamics will tell you, look, I mean, these ones can occur, this needs to be excluded. Out of these ones, you get a diagram that looks very complex. So for each chemical reactions, now you get one line. And basically what you're interested in your reactor is the cross-section of the lowest energy path that you need to take. Okay? which is basically, you see the dots here, basically the one reported in this diagram. So what we did is, instead of having about 100,000 plots, we summarize all of that. And we say, look, for the pressure and the temperature we are interested in, I'm going to compute the probability of making a volatile component or not, which is the ratio of the enthalpy of formation of a gas phase versus the solid. If the value is larger than 1, I can make a volatile component. If the value is smaller than 1, I will make a solid. Then you end up with a plot that looks like this. So this is a chemistry you will be using versus the probability of making either a volatile component or a solid. Ideally, if you want to use a specific chemistry during your plasma, you would like to be really on this side. High probability of making a volatile component, very low probability of making a solid. The dots is basically the main value, because you see here you have a lot of different values. So that's the mean value of the system. And then actually the line shows the deviations you can get out of that. So is there any room for you during your etching process to control your process? So if you have something very deviated, very broad like this, it tells you, look, there are pressure and temperature conditions where you can make volatile components, and other compositions where basically the probability is very weak and you're going to make solids. So you observe, for instance, if you use carbon monoxide, then you have what we call a process of integration. There's a window here that you can use. If you use CO2, no way. If you use the halogen components, so HCl and HBr, most of the time you generate volatile components, but this is too aggressive for the steel which is present in the reactor, so forget it. Chlorine-based components, well, you're somewhere at the border. Bromine chloride is slightly better than this one. Any component having oxygens here is leading to redepositions in your system. You see hydrogen is, if this is hydrogen rich, so the low plasma conditions, very weak ionizations in your system, well, basically that is going to generate miseries. You're going to form hydrides, while an hydrogen rich radical, so high voltage in your plasma, is going to lead to the formation of a volatile component. So with all of this, I hope I somewhat convince you that these simulations and the Schrödinger equations actually used for something useful. And with this, I thank you for your attention. So if you have questions, feel free. If not, well, I wish you all the best. Enjoy your lunch. And good luck with your exams at the end of the year. Thank you. Last thing, I mean, if you have to complain about the way I teach it, you have to do it to Stefan again. Okay? Hopefully not too much. Also, if you have ways to improve this, if you didn't find this interesting because you would like to see something being done differently, let me know. I will try to change it for next year. Thank you.